Hello folks, in this video we're going to talk about magnetism. What is it? And what is its relationship to electricity? We've already talked about one of the forces of nature as being electromagnetism, so that must mean that they're somehow related. So we'll take a look at that. What are the origins of magnetism? Where does it come from? What's going on at the atomic level? And then we'll end the video with just a mention of a few applications of magnetism and electromagnetism, of which there are many. So, what about magnetic interactions? What do we know about magnetic interactions? You probably know, of course, that there are north and south poles, magnetic interactions, and that there's an attractive interaction between the north and the south poles of a magnet. So here we have, in this diagram, we have a bar magnet which has a north pole and a south pole. Okay, and we know that the north pole and the south pole are attracted to each other. If you bring two magnets together such that the north and the south are adjacent, they'll be attracted. But if you bring two magnets together where the like poles are adjacent, like the north and north or the south and south, we'll see repulsion. Okay, which of course is not unlike electrical charge. Positive charges are attracted to negative charges. Positive charges repel positive charges. Negative charges repel negative charges. So there seems to be a similarity there. But there is one big distinction between electricity and magnetism. In electricity, we have individual charges. We can isolate positive charges and negative charges. In magnetism, we can't do that. If you break up a magnet, shown here, if I take this big bar magnet and I break it up into two magnets, then what's going to happen is I'm still going to have a north pole and a south pole in each of those magnets. Now these two will be attracted to each other, of course, but I can't isolate a north pole. I can't find a substance that is just a north pole or just a south pole. I can break it up and I can keep breaking it up, but we're going to find that they're together. And that is the question of monopoles. A monopole would be a substance that just is a north pole or a south pole, just like we have an ion or an electrical charge. So you can have cations, which are positively charged, and you can have anions, which are negatively charged, right? You can isolate those, but we can't have monopoles, all right? That's been a search for monopoles for ages as scientists have tried to discern whether such things actually exist. There are some theories that predict the existence of monopoles, but they've never been observed. So that's one big difference between electricity and magnetism. We cannot isolate the north and the south pole into monopoles. All right, and though we've got that difference, just like we have electric fields, as we talked about in the previous video, we also have magnetic fields. And that means we have field lines, just like we have in the case of charged particles. So this diagram here very simply shows the magnetic field lines for a magnet and the directions of those lines, of course, going from the north to the south pole. Again, this is not dissimilar from the kinds of field lines that we talked about with regard to charged particles. In fact, you probably, even in elementary school, may have done the simple experiment where you would get magnets and you would pour iron filings over the magnets or over a surface under which the magnets were placed, and you would see the field lines associated with that. No doubt you've seen that. So we have magnetic fields, which are the magnetic fields are the purveyors of the magnetic interactions, just like we have electric fields. All right, so how are the two related? Well, it turns out you can create a magnetic field by moving a charged particle. That's why we call it electromagnetism. They're very closely related, and in fact, they are related through the same general force in nature as I mentioned earlier. But if you have a moving, so this particular diagram shows an electrical current flowing through a conductor, a wire, okay? And what we're going to see is if you were to put in this diagram a compass there, you would notice that there would be a magnetic field generated by the movement of the electrical charge, and the compass needle would certainly indicate the direction of the field associated with that. So if you just have a straight wire, you would get a circular magnetic field lines surrounding it. Now, your textbook actually goes into more detail about the different configurations and geometries of wires and the magnetic fields associated with it. Suffice to say, for this discussion, we just know that anytime we've got electrical charge moving, we're going to generate a magnetic field. So there's your relationship between the two. So a moving electrical charge will generate a magnetic field. A moving magnetic field adjacent to a conductor, electrical conductor, will generate currents. And that's a principle behind generators, and we'll talk about that in a little bit. So again, the key here is a moving charge will generate magnetism. And hence that relationship is why we put together the two in electromagnetism. All right, so what are the atomic origins of magnetism? We've already talked about the fact that charged particles and moving charged particles create magnetism. Well, so you might expect then that when we get to the atomic level, electrons and protons we know are charged particles, and therefore the movement of those should actually then create a magnetic moment. It turns out the neutrons also have an intrinsic magnetic moment as well. So the electrons, protons, and neutrons have this thing called spin magnetic moment, which is actually not due to spin. That name is a historical artifact. But there is a magnetic moment associated with each of these particles that exists within an atom. There's also electron orbital motion, and we'll talk about these are not orbits. We'll make that clear when we get to discussions of atomic structure. But there is a magnetic moment associated with electron orbital configurations as well. So that's something that we'll talk about as well. All of these together create the magnetic properties of the atom. Now, one thing to note, though, is that, of course, if we've got electrons or protons and neutrons, why don't all atoms have magnetic moments? Well, in a lot of cases, we have a situation where all of the magnetic moments kind of cancel each other out to the point where there really isn't an intrinsic magnetic moment associated with the atom. In particular, when we talk about, for example, atomic structure and electrons, if all of the electrons in the atoms are paired up, and we'll learn a little bit more about this when we talk about atomic structure, but electrons like to be paired up, if you will, and if all the electrons are paired up, all of their intrinsic magnetic moments cancel each other out. And you got a situation where you might have one magnetic moment going in one direction, another going in the other direction when they're paired. And so when they add the two together, they cancel each other out, and therefore you get nothing. And if we have that situation where all the electrons are paired up in an atom, that's called diamagnetic. The atom is said to be diamagnetic. If we do have unpaired electrons, for example, if I have a situation where I've got two electrons with magnetic moments in the same direction, then I'll get a net result magnetic moment, and that's said to be paramagnetic. So just to reiterate, unpaired electrons create a net magnetic moment, and those unpaired electrons then in that typical situation create a property called paramagnetism. And I'll give you an example of that in a few minutes. And then of course we have the more commonly known property of ferromagnetism. When you think of permanent magnets, that's due to ferromagnetism, and that's more of a property that encompasses the entire substance. So what happens in ferromagnetism is that you've got domains within the substance, like iron, for example. You have these domains, and normally in this illustration here, the arrows are pointing in the direction of the magnetic moment, the magnetic field. Normally they're oriented in different directions, and so they kind of cancel each other out as a result. But if we magnetize it, so if we bring an iron bar or something like that in proximity to a permanent magnet, the permanent magnet will cause the individual domains. So each of these regions that we've got here is a domain. And again, normally those domains are oriented randomly, so no net magnetic field. But if we can orient them, how do we orient them? We bring them in proximity to a permanent magnet, and that magnet causes them to orient themselves so they're more or less in the same direction. At least the net result is that we get a magnetic field in that same direction. And those domains will retain that orientation after that magnetic field is removed. And so that's what leads to a ferromagnetic substance. Again, iron is a prime example. Ferro represents iron. So that's what we're talking about there at the atomic level, what's going on. All right, so let's look at a video here where what we're going to see is Physics Girl actually looking at oxygen, and liquid oxygen, as a matter of fact. Of course, the oxygen that we're familiar with is in the gas phase. We're inhaling oxygen. Oxygen is necessary for life. But if you cool oxygen down to a temperature of roughly 90 kelvins, that's 90 degrees above absolute zero, 90 kelvins, then it will liquefy. You may be aware of liquid nitrogen. That's another one that's more commonly used. Liquid nitrogen, cooled to 77 kelvins, will liquefy. So if you're using liquid nitrogen, it's at 77 kelvins. So that nonetheless, let's take a look at Physics Girl and what she's doing with liquid oxygen in this video.
This episode is supported by 23andMe.
I'm so excited. I didn't think there was going to be an opportunity for, like, you get to handle liquid oxygen.
Oh, yeah.
Throw the switch down.
For the liquid oxygen.
Okay.
And then lift the switch.
I feel nervous. I don't know why.
I'm here at MIT with one of the technicians from the physics demo group, preparing to pour liquid oxygen over a magnetic field created by some super strong electricity. Let me repeat that. Liquid oxygen. I've never seen liquid oxygen. And they let me pour it. By the way, I'm Diana and you're watching Physics Girl.
Okay. And then... Oh my gosh. I can't believe this demo.
It is really cool.
I was freaking out because the liquid was just hanging there between two magnetized pieces of metal. Liquids aren't supposed to do that, in my experience. But this liquid was just hanging there in a magnetic field created by electricity. And as soon as you turn off the electricity, well, let's see what happens.
There's no surface tension effect here. That's amazing.
And as soon as I turn it off.
Oh my gosh!
Can I do it again?
In all my time at MIT, no professor ever did this demo for us. So disappointing! Because the physics here is really cool. First thing, there are electromagnets, which are made by running electricity through coils of wire.
Two coils that when we pass a DC current through them, it's going to create a magnetic field between these two giant pieces of metal. These are what are becoming magnetized
Okay.
by the DC current running through these coils.
The result is a strong magnetic field around the metal pieces, but most importantly, in the gap between them. It's just like a strong magnetic field between two permanent magnets, except you can turn it off. Now, if you poured liquid nitrogen or water or alcohol in between the two pieces of metal, you wouldn't get any of it hanging around and partying. You might get a few droplets of water sticking to the surface because of surface tension, but though the liquid oxygen has surface tension, it's not what's causing the liquid to stick to the metal here, because the oxygen boils away too quickly at the interface. It's the Leidenfrost effect. Then why is the oxygen hanging out? Well, it's because different materials have different responses to external magnetic fields. Your face is pretty unresponsive to a strong magnetic field. Iron is visibly responsive to an external magnetic field. I don't recommend doing that with your neodymium magnets. Hot iron acts differently, as we'll see when we heat up this piece of metal with a blowtorch. Yeah, stay tuned for that. But liquids don't usually visibly react to magnetic fields, and yet liquid oxygen clearly does. By the way, liquid oxygen is oxygen cooled down below 90 Kelvin. In Fahrenheit, that's when your spit freezes way before it hits the ground. So liquid oxygen has this property called paramagnetism. It reacts mildly to an external magnetic field, and all the little mini magnets that make up the oxygen align with the external magnetic field. These mini magnets I'm talking about are basically the little magnetic moments of the electrons in the oxygen's atoms. You can really think of a magnet being made up of tiny, 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 tiny little magnets all aligned in the same direction. But in a paramagnetic material, as soon as you turn off the external magnetic field, all those little mini magnets go back to pointing in random directions. Now, iron in turn has ferromagnetic properties, so all of its little mini magnets align strongly with an external magnetic field, and even keep some of that alignment after the field is removed. But there's a point when even the mini magnets in ferromagnetic materials won't align, and it's when you get them hot enough.
Yep, so this is just a little magnet, and then we have a thermally insulating plate so that we don't damage our magnet.
Oh, that's okay, that's not stuck on there that hard.
No. Yep, just loosely.
Yeah. Okay.
So it takes a little while.
We're heating the iron metal here past what's called the Curie point. There's too much energy, too much random motion of the magnetic moments for them to align. And so the iron no longer sticks to the magnet. This is just like how it's impossible to get a bunch of preschoolers to line up if they have a ton of energy. But if you freeze them, I mean metaphorically, if you let the iron cool back down,
Cools, it will actually be redrawn to the magnet.
the Curie point of iron is around 1043 Kelvin, which is incidentally around the temperature when iron starts to get hot enough to emit visible light, which is why it's glowing here. I really enjoy these demonstrations, and we tried some other demonstrations and some other stuff with these demos.
Can you just like, oh wow, there's a big spark there too.
So that's a back EMF. We actually have one that's will do a huge back EMF when you lift it.
Oh.
We could just wheel that one out.
We did wheel that out. I'm gonna save that demo for next week though. Thank you to the technical services group at MIT. They were amazing. They made all of this possible. Thank you guys for watching this video. Subscribe if you want more physics, and hit the notification bell if you want to know when my videos come out. And happy physicsing!
So in that video, we got to see that oxygen, liquid oxygen, was paramagnetic, meaning it has unpaired electrons, as we said before, and it will be suspended between the poles of a magnet. We also got to see a discussion of the electromagnet, which was what was generating the magnetic field. An electromagnet is, as we mentioned earlier, a moving charge will generate a magnetic field. So you can generate a magnetic field. You can make a magnet called an electromagnet by flowing charge through wire surrounding a metallic object. So that is an electromagnet. In that situation is what we had. Now electromagnets are very important in lots of applications if you just kind of look it up. But one I just want to talk about right now is the application of an MRI here, which is depicted in this little illustration. I'm sure some of you have experienced an MRI as you've had to have some kind of issue diagnosed where basically you are put inside of a giant magnet. That's what you have there is a giant magnet with a very large magnetic field, much larger than a typical magnet that we're used to having around playing with when you're a kid or whatnot. So it is a very, very significant magnetic field, and that's why you can't have any magnetic objects with you when you're going through an MRI. A magnetic resonance imaging is what that's called in that process. In order to generate the magnetic fields necessary for an MRI, we need to invoke something called superconductivity. All right? Superconductivity basically refers to the flow of electrical current through the system with no resistance. Now you remember we talked about resistance in a previous video and talked about Ohm's law and the current flows depending on the resistance. A superconductor has no resistance. Now normally in order to achieve a superconducting state, you need very, very cold temperatures to do that. It doesn't work well, certainly it doesn't work well at room temperature, and that's actually a pretty significant area of research is to develop superconducting material that will function as superconductors at much higher temperatures, because there are some wonderful applications associated with that if we could actually have superconductors that operated at higher temperatures than normal. So what this usually means is that you need to have temperatures pretty close to absolute zero in order to achieve superconductivity. And so in these superconducting magnets, you have both liquid nitrogen, which has a boiling point of 77 kelvins, 77 degrees above absolute zero. So when you have liquid nitrogen, so that gets pretty cold. But even that, the liquid nitrogen is actually used to insulate something that's even colder, and that's liquid helium, which has a boiling point of roughly 4 kelvins at normal atmospheric pressures. That's really, really cold. In fact, helium is the substance that has the lowest boiling point of any known substance. Even though helium is a larger atom than hydrogen, as we'll talk about a little bit later on, hydrogen exists as a diatomic molecule, whereas helium does not. Hydrogen exists as H2. Helium is just what we call monatomic. And because it's smaller, it has a lower boiling point. And so that means we need temperatures that low in order to achieve stable superconducting status to generate the large magnetic fields necessary for MRI machines. Now, you may be aware of the fact that we're going through a time right now where there's a real concern about a helium shortage. Helium is a non-renewable resource. Helium is mined, it's trapped underground, and so it is mined, but it is not something that's replenishable. So if we run out of helium, we're out of helium. And while that can be a problem for party balloons, the big problem is cryogenics, because we need these super cold temperatures in order to do a lot of the superconducting research, and also for things like MRI machines. Until we can develop materials that are superconductors at higher temperatures, we have to rely on having a supply of helium that can be used in those situations. So that's a big application of electromagnets and actually helium in the use of MRI machines. There are lots of others that you can find if you start looking into it. And of course, in addition to that, electromagnetism is used in switches, solenoids, if you've heard that term used before, motors. It's important for motors, generators. For the generation of electricity, You have portable generators, of course, and you may have some with your house in case the power goes out. You hook it up so that you can actually use that to generate power for your house during a power outage. But it's actually in the generators or in fact, frequently called alternators in your car. Will actually keep your battery charged in the car. As the car moves, it's going to generate electricity that can charge up your battery through a kind of a generator process. So, in the basic process of electricity generation, this in fact is how electricity is generated in power plants, coal-burning power plants, nuclear power plants, wind turbine generated power, hydroelectric power generated by water flow. There's some mechanical process. In the case of something like a coal burning power plant, coal is burned, all right, and the heat released when it's burned is used to boil water, to heat up water. The water boils, and the pressure of the water actually then causes a turbine to turn, and that turbine turns, causing a moving conductor through a magnetic field, and that moving conductor moving through a magnetic field generates electricity, right? So remember, if you've got electricity moving, charged particles moving, that generates a magnetic field. If you have a magnet moving, you can generate electrical current. And so this illustration here shows that. It's kind of a handheld device, but basically you've got a conductor here, and you can turn that conductor, it's between the poles of a magnet, you can turn that conductor through the poles of the magnet, and as the conductor rotates through the poles of the magnet, it causes an electrical current to be generated, which can then be, in this particular circumstance, the current's measured in a meter, but that's how electricity is generated in a power plant. Heat from the coal in a coal burning plant, heat from the coal causes pressure to turn a turbine that generates the electricity through that generator. That's how it works. Coal burning plant does that. Nuclear power plant, for example, also does that, because in a nuclear power plant, again, the process is the nuclear process generates heat, which heats and boils water, and the water at high pressures, the steam from the water turns the turbine, which generates the electricity. So once you get past the source of the fuel, the source of the energy, coal burning generates heat, nuclear power generates heat. The turning of the turbine is what generates electricity in both. Wind power, you've got a windmill that's moving and rotating. That's also causing a turbine to rotate, which generates electricity. So same idea in those particular ways of generating electricity based on, again, electromagnetism, the relationship between electricity and magnetism. So that's just a few applications. There are a lot of applications. I would certainly encourage you to research these applications, particularly important as we need to be concerned about possible sources of energy in the future. So have fun with that, and as always, ask questions.